So next, we're going to look at the quotients of polynomials. Now we know that for rational functions, we have f at x is equal to p at x over q at x. And p at x and q at x are both polynomial functions. Q at x cannot equal 0. So an example would be 2x plus 1 over x squared minus 5, or even 3 over x. Okay. However, if I had y equals 3x squared plus 1 over the square root of x minus 1, this is not a polynomial because if I rewrite this, it's x minus 1 to the power of 1/2, and 1/2 is not a natural number, so this is not a polynomial function. So today we're going to be looking at asymptotes. Asymptotes are values that make the denominator equal to 0. So the function cannot exist at that point. So vertical asymptotes, in other words, occur when the denominator of the function is 0. So if I had f at x equals p at x over q at x, there's going to be a vertical asymptote, x equals a, if q at x equals 0. Okay, so if the denominator and numerator are equal to 0, both the denominator, then we're going to have a whole at x equals a. But if it's just the denominator, then there'd be a vertical asymptote at that spot. So for horizontal asymptotes, so say I have f at x equals h at x over g at x. There's a few reasons why we may have a horizontal asymptote. And there are a few different types of horizontal asymptotes we can have. So your horizontal asymptote, as we saw in the last lesson, will be y equals 0 if the degree, so remember the exponent, in the denominator is greater than the degree in the numerator. Now, y is going to equal the coefficient of the highest degree in the numerator divided by the coefficient of the highest degree in the denominator. And this is going to be the case if the numerator and the denominator have the same degree. So an example would be if I have 3x squared over 2x squared, then it would be 3 over 2. And there's going to be no horizontal asymptote if the degree in the numerator is higher than the degree in the denominator. So for example, if I have 3x cubed over x squared, we would have no horizontal asymptote. Now, an oblique asymptote. An oblique asymptote is a slanted line. It can have any slope. So oblique asymptote would look something like this. And then maybe my function would look like this. The oblique asymptote can have any slope, and a function f at x has an oblique asymptote if and only if the degree in the numerator is exactly 1 higher than the degree in the denominator. So it has to be exactly 1 higher. So for example, if I have x squared minus 4 over x, the degree here is 2, the degree here is 1. Or if I have 3x to the power 5 plus 3x minus 4 over 2x to the power 4 plus 5x cubed. The degree is exactly 1 higher. Okay. So let's take a look at a few examples here. So for the first one, we have y equals negative 3x over x minus 4. So we're going to have a vertical asymptote at x equals 4 and a horizontal asymptote at negative 3 over 1. So y equals negative 3. Now the next one, we have y equals x over x cubed plus 8. So we're going to have a vertical asymptote where x cubed plus 8 cannot equal 0. So we would find the cubed root. So x at x equals negative 2. And then if we look at the degree, it's higher in the denominator. So we have a horizontal asymptote at y equals 0. Now for this next one, we have y equals 4x plus 3 over x minus 2. We're going to have a vertical asymptote at x equals 2. And for the horizontal asymptote, since the degrees are the same, we're going to have a horizontal asymptote at 4 over 1, so at 4. Okay, so for this one, we have a degree of 2 and degree of 1. It's exactly 1 higher. We have a vertical asymptote at x equals negative 2. For the horizontal asymptote, we're going to write none. But we have an oblique asymptote. So how do we find the oblique asymptote? We're going to take our function x squared over x plus 2, and we're going to do exactly that. We're going to divide. We know this is division. So we have x squared. Now remember, we need placeholders for 0x and for the coefficient, and we're going to divide by x plus 2. So when we divide, we can get x, and then x squared plus 2x, and then we subtract negative 2x, and then you get minus 2, multiply, and you get negative 2x, 0 remainder. So you're going to have an oblique asymptote at y equals x minus 2. So this is your oblique asymptote. Now what about for this next one? We have y equals x squared minus 25 over x minus 5. Well, let's see if we can factor this. Notice in the numerator we have a difference of squares. So we're going to have y equals x plus 5, x minus 5 over x minus 5. We're able to cancel these out. So we're left with x plus 5. Because we're able to cancel these out, we have a line, y equals x plus 5. However, there's going to be a hole at x equals 5. There's no vertical asymptote, and we also do not have a horizontal asymptote. And finally, we have y equals x plus 1 over 2x squared plus x minus 1. So if we were to factor this, we would have x plus 1 to x minus 1. So we're able to cancel these out, which gives us 1 over 2x minus 1. So we would have a vertical asymptote at x equals 1/2. Now if we look at the original, do we have a horizontal asymptote? So we do have a horizontal asymptote. The horizontal asymptote is going to be at y equals 0. And then because we crossed out the x plus 1, we're going to have a hole at x equals -1.